Hello and welcome to my channel. In this video we are going to learn how to code a unit for skin lesion segmentation. For this project we are going to use the dataset from the ISIC 2016 challenge. First, we start importing some libraries. Now we have to define our dataset class. It will take both the paths of the images and the masks, as well as their corresponding transforms. The length function will simply return the length of our images directory. We also define our getItem function, which will take an index as an argument. We're going to use this index to find the image name, and we're going to find the path of the image by joining the path of the images directory with the image name. We use the image name to match it with its corresponding mask. Now we have to load our image and mask. Additionally, we will hold a copy of the image in the variable RawImage that will not be normalized for visualization purposes. If there are transforms, we apply them to the image and the mask. Notice that we do not want to normalize the raw image. This is for visualization purposes. Using the NumPy library, we transform our mask into binary. We do it by filtering all the values that are greater than 0 and transform them into 1. Subsequently, we transform our mask into a PyTorch tensor. Finally, we return the normalized image, the mask, and the raw image. The next step involves normalizing the images for efficient model training. We start by defining our images and masks directories. Now we define a transform that will resize the image to be 256 by 256, and we also transform them into torch tensors. Now we initialize a dataset using the normalized transform, and we also create a data loader. Finally, we calculate the mean and the standard deviation of the whole dataset by simply calculating the cumulative sum of the mean and standard deviations of all the images in the dataset and dividing it by the number of samples in the dataset. These are the results that were obtained. Now that we have calculated the values for the mean and the standard deviation of the dataset, we can define the transforms for our images and masks. The images will be resized and normalized. The mask will only be resized. With these transforms, we can define our dataset and our data loader for the training. With this, we can explore the dimension of our data. Notice that for the images, there are 3 color channels: red, green, and blue, while for the masks, there's only 1 because they are in grayscale. Now that we know that our data loader is working, we can visualize one batch of data. For this, I define this function that will allow you to explore an image, the normalized image, and the segmentation. This is the result of the visualization. The normalized images are the ones that are going to be used in the training process. Normalizing the images brings some benefits, for example, stabilization during the training process. Feel free to stop the video at this point to learn more benefits of normalization. Now let's build our model. Let's first build the building block, the double conv class. Notice how we are creating a sequential block with 2 key patterns: a 3x3 convolutional layer, a batch normalization layer, and a ReLU activation. We do this twice in sequence, which helps the network learn more complex features. The padding of 1 in our convolutional layer ensures we maintain our spatial dimension. Using inplace equal true in our ReLU layer saves us some memory. Now let's define our model class. The architecture will have 5 main sections. The first one, an encoder path or downsampling path, a bottleneck section, a decoder path or upsampling path, skip connections, and the final output convolution. In the encoder, we are progressively reducing spatial dimensions while increasing our feature complexity. First layer starts out with the input channels, which is 3, and then goes to 64. Then from 64 to 128. From 128 to 256, and from 256 to 512. Later in the forward method, you will notice how we use max pooling to downsample, halving our spatial dimensions each time. The bottleneck is where we hit peak feature complexity, 1024 channels. This is where the network captures the most abstract representations of our input. Here in the decoder is where the magic happens. We use transpose convolutions to upsample, and then in the forward method you will notice how we concatenate with our skip connections from the corresponding encoder levels. But why we use skip connections? Well, basically they help preserve spatial information that might get lost during downsampling. Finally, we create an output convolutional layer. Now, in our forward method, we're essentially 1. Encoding our input, 2. Going through the bottleneck, 3. Decoding back up with skip connections, and 4. Generating our final output. With our architecture defined, we create an instance of our model. We also create a dummy input tensor and pass it through our network just to double check that we are obtaining the desired output shape. In these lines of code, we are creating our test and training data loaders to train our network. Now let's initialize our unit model. We can easily specify the input channels, which by default is 3 for RGB images, and the output channel, which by default is 1 for binary segmentation. We are using binary cross entropy with logits lost. It is perfect for binary segmentation tasks. The with logit part is crucial. It combines a sigmoid activation with binary cross entropy. This means more numerically stable, handles raw unscaled predictions, and prevents you from manually adding a sigmoid layer. For the optimizer, we're using the Adam optimizer with a learning rate of 0.001. Let's talk about device selection. We're using MPS, which stands for Metal Performance Shaders, which is Apple's answer to GPU acceleration. This is a game changer for Mac users. It leverages Apple Silicon's GPU capabilities, giving us better performance on Macs with M1, M2, M3, and M4 chips. For the training, we first move our model to the GPU. We're running 15 epochs. Think of each epoch as a complete journey through our entire training dataset. In the training phase, we set the model to train mode. We also initialize our loss tracker, and we iterate through our data. For every batch of images and mask, we move the data to the device. We also get the model predictions and we calculate the loss. We zero out the previous gradients and backpropagate, and then update the model weights. After each epoch, we also print the training loss. After training, we switch our evaluation mode to model.eval. This will disable gradient computation and assess our model performance on unseen data. We're essentially checking how well did our model learn. After training, we can visualize our losses. We can notice how they have been decreasing during the training process. I also created this function to visualize our predictions. Here we can compare the ground truth with the segmentation of our network. We can evaluate the performance of our model using dice coefficient and intersection over union. In the case of dice coefficient, the formula is measuring how much do the predictions overlap with the ground truth. The result ranges from 0 to 1, where 1 is a perfect prediction. In the case of intersection over union, imagine drawing two shapes on a piece of paper. The intersection would be where the shapes overlap, and the union the total area covered by both shapes. Intersection over union tells you, out of all the area these shapes cover, how much do they actually match. And again, the score ranges from 0 to 1. We evaluate model performance using the test dataset. At the end, the average dice coefficient was 0.82, while the average intersection over union was 0.69. We conclude this video by saving our model. I hope you enjoyed this project and subscribe to my channel.